Sorry about the lateness, guys.
Oh, you're fine.
Basically what happened is I got hooked up with the emails, and because I got hooked up with emails, I got into this. It's like you think I could do one more, and all of a sudden it's 9:30. So I apologize for that.
No, you're fine.
Yeah, scary issues. I told you, I think last week, that I had a student that tested positive for COVID.
Yes.
What happened is I spiked the temperature on Sunday night.
Oh my gosh.
So I have been spiked the temperature on Sunday night. It went away. So all yesterday, I've been trying to deal with the COVID testing. I'm negative. I got tested yesterday at 5 o'clock, so I'm negative. I'm good. I just kind of like wanted to keep you up to date on why I may not have gotten to things. I did not get to your email. If anybody has a current issue, please shout it out right now. Okay, that's one point. The second point I really wanted to emphasize today, we're going to go through acids and bases. That's going to be the beginning of the end of our review process. Okay. When we get into gas laws, the first thing in gas laws we're going to get into is the kinetic molecular theory. I'm going to go into that in detail, and you had better be prepared on the test to be able to explain it. It's not an easy concept. So if you have friends that have been skipping these because they've been all review and what they would call useless, please tell them that, if you could tell them that this stuff is going to be important coming up and they haven't had it, it may be something to them. Or on the other hand, if you want to be selfish like I am, you may want to just leave it and just let them flounder on their own. But you guys are nice people. Is that true? Kevin, you're a nice person, aren't you? You'd tell somebody, wouldn't you? Yeah. Nothing more needs to be said.
I'm still recovering from last night and the Stanley Cup.
So am I. So am I. Hey, did you stay up for the two overtimes?
I've stayed up for every period.
Kevin, I got to be honest with you. I fell asleep for the first overtime. I managed to wake up just in time for the second one, and I was not happy. On to the Rays now.
Sad.
I'm sorry, Kevin.
I was sad. I stayed up till like 3 a.m. just sitting there watching highlights and stuff.
On to the Rays, Kevin.
Yeah.
Okay, guys, I'm gonna quickly get through acids and bases. All right. Anybody have any questions before we go on?
Have our labs been better?
Have your labs been better?
Yeah, like because you were worried about our lab book and you kept saying stuff about it. Yeah.
Kevin, I haven't touched it yet. I'll be honest with you, I haven't looked at it, and I'm as I said in my notes, I believe I'm really looking to the ones for this week. I believe you had to do what we're doing this evening is going over standardization of the base, right?
I'm not sure.
Okay, that's the one that's the notebook that I'm really interested in. Okay. I'll look through them. I will look through them. It's number 15 on the list, Kevin.
Roger that.
Hi, Brooke. How you doing? Is Brooke in here? Yeah, she's in here. She's being quiet. Hi, Brooke. Everybody see the screen? Acids and bases. Everybody see this?
Yeah.
Okay. Ooh, isn't that lovely animation? How it goes from blue to red, just like acids and bases do. Ooh, I get chills every time I hear that. So what we're going to talk about, we're talking about properties. We're going to talk about the definitions of an acid. There are 3 basic definitions that you need to know. We're going to go through pH conversions, the amphoteric nature of some acids and bases. We're going to go through titrations, and then I'm going to mention equivalent weights. So, general properties. Acids are sour. How many of you have ever bitten into a lemon? Nobody? Nobody has ever bitten into a lemon.
I have.
What did it taste like?
Really acidic.
What did it taste? You don't,
A
when you're a
lemon?
baby, when you're a baby, you don't say it tasted acidic. What do you say it tasted?
I don't know, like a sour lemon.
Sour, thank you. Thank you very much. Sour. Sour is what acids taste like. So if you taste something that's sour, chances are you've got an acid. On the other hand, has anybody ever done or had to take painkillers?
Yes.
I'm talking about the opiates, the big ones.
Yes.
Cassidy, what did it taste like?
Nothing. It was a pill, so it wasn't really in my mouth for long.
Okay. I've got a hint here, Cassidy.
It's bitter.
Seriously, has anybody ever tasted a painkiller? Opioids are bases, so they have this bitter taste to them. Acids turn litmus blue. Bases turn litmus red. That's wrong. Wrong, 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 wrong. Wrong, end show. Acids turn litmus red. Bases turn litmus blue. I don't know how that got in there. Okay. Okay. Acids turn litmus red. Bases turn litmus blue. Acids are colorless for phenolphthalein. Bases turn phenolphthalein fuchsia for those of us that are color inclined, or purple if you don't, pink purple if you don't like that. Anybody know the difference between corrosive and caustic? Anybody? I literally spent an afternoon. This is how boring I am. I spent an afternoon trying to discern the difference between corrosive and caustic. Do you know what I finally came up with? If it's an acid, it's corrosive. It's a base, it's caustic. Basically what that means is it reacts very, very strongly with things and decomposes them. Both acids and bases are electrolytes. Acids have a pH less than 7. Bases have a pH greater than 7. Acids, if they're inorganic, if acids are inorganic, are usually in their elemental and their molecular stage are gases. They're gases or liquids. When we get into organic acids, all bars are, it doesn't hold true. Organic acids, to a large degree, are solids. But inorganic acids are usually gases or bases. Bases are usually solids if they're inorganic bases. Bases feel slippery. Couple things we need to know. Typical reactions. If you react an acid with a base, it forms a salt. Acids react with carbonates to form CO2. You should be either writing these down or noting where it is in the PowerPoint so that you can access these later. And you know this one, you know carbonates form from acids and, CO2 forms from acids and carbonates because you've done the experiment. You've done the volcano experiment where you put bicarbonate and acid together, it makes all kinds of bubbles. Those bubbles are carbon dioxide. Acids also react with metals. They react with active metals to make bubbles, which are hydrogen gas. Are we good with these? These are basically the three reactions I want you to know about acids. They react with carbonates and bicarbonates to make CO2. They react with bases to form salts. And they react with active metals to form H2. If you remember back to the experiments, acid does not react with copper. It will not react with gold or silver. Those are inactive metals. But it reacts with things like magnesium, sodium, barium. It will react with those to make hydrogen gas. Bases, on the other hand, react with acids to form salts. Funny enough. They react with CO2 to form carbonates. So basically, we're talking about for the first two, we're talking about opposite reactions. And they react with salts to form insoluble hydroxides. In other words, if you put a base like barium hydroxide and you react that with something like copper chloride, that will react to form copper hydroxide, which is a solid. Okay, questions about that, guys? You are responsible for the properties of acids and bases. Any questions before I go on? Fair enough. We're going to deal with three basic definitions. Before Arrhenius, chemists tried to assign acid and base properties based upon oxygen. What Arrhenius did was he kind of switched the thinking around, that instead of oxygen, it's the hydrogen that's causing acids and bases to be created. So Arrhenius's definition, acids produce H plus or H3O plus. I'll get into hydronium in a second. Bases produce OH minus. So that's all Arrhenius said. If a compound produces H pluses, it's an acid. If that compound produces OH minuses, it's a base. Well, that didn't satisfy all the things that we knew were acids and all the things that we knew were bases. That definition didn't work some of the times. For example, we know that ammonia, NH3, when it's placed in water, is a base. We dissolve ammonia in water, it bubbles up, and when it bubbles up, some of the ammonia gets dissolved in the water, and if we put litmus in there, the litmus is blue. So we had to come up with another definition, and Bronsted-Lowry did it. And he said that, okay, acids are going to donate H pluses, and bases are going to accept them. But that didn't satisfy everything, because as we evolved, we got into more and more organic compounds. And so we had to revise the definition a little bit. And Lewis said that acids accept an electron pair, bases donate an electron pair. If you are going on to organic chemistry, you're going to need this, because organic chemistry mechanisms involve moving electrons from one compound to another. And you've got to know what happens, what tendency a compound has, whether it can accept an electron pair or whether it can donate electron pair. So we're going to use, for the most part, we're going to use the Bronsted-Lowry definition. Arrhenius only occurs in water. We can use any solvent for Bronsted-Lowry. And Lewis is again used in organic chemistry with a wider range of substances. So you need to know the three different definitions, but more specifically, we're going to be dealing with the Bronsted-Lowry. Now, I told you a little bit about a hydronium ion a second ago. What happens when, I'm going to actually end the show right here and put in another, I'm going to end the show and put in another slide. Nope. It doesn't want me to do that. New slide, thank you. When we have a hydrogen donated, right? Most of the time, it's going to be in water. So that hydrogen is going to react with water to make something called a hydronium ion. And really and truly, it doesn't really matter, because ultimately what happens is this eventually will react with something, lose its positive charge, and get converted back to water. But you have to realize that this overall reaction is happening, that H pluses are really H3O pluses. I use them interchangeably when I talk. So if I say H plus, think in your heads, okay, it's also an H3O plus, because it's H plus because that's what the acid is donating. But if it's donating it in water, it exists as H3O plus. Does that kind of make sense to you? Are we good with that concept?
So when H is donated in water, it's H3O.
Correct.
That's the only time.
Yes, yes, basically that's what it is. But you have to understand that, and I'm going to get to this when I get to the acid-base reactions. What's happening is the acid exists like this, but then this will react with OH minus. Okay. To make two waters. Does that make sense, Kevin? Kevin? Some?
Yeah, some.
Don't overwhelm your head with it. It's not really that important a concept. All it is important is that you know that this does happen, that you do get H3O pluses.
Oh,
Okay?
so if you add the H, it gets H3O, and if you add an oxide, it breaks down back to water.
Yes. Okay. If I do this, then I get okay. Do you see what I'm saying, Kevin? Ultimately, if I did this, okay, because I've got this on the reactant side and the water's on the product side, they would cancel out, correct? And ultimately, I've got this. Okay? Does that make sense to you now, Kevin?
Yes.
Okay. So we're going to go slideshow, current slide. All right. Now, when you react an acid with a base, each and every time you do an acid-base reaction, you get the same two products. You make water. Every time you mix an acid and a base together, you make water. It's a double replacement reaction. So if I give you this reaction on a test, if you call it a double displacement, you get credit. If you call it an acid-base reaction, you get credit. Because what's happening is the acid is reacting. The HCl is reacting with the OH to make water. And what's left? The only thing that's left is the Na is reacting with the Cl to make NaCl, or my salt. A salt, by definition, is the product of an acid-base reaction. That is what a salt is. It's just that we use NaCl as the common, you use as its common term, table salt. Okay, Kevin. I mix these two guys together. I mix these HCl and magnesium hydroxide. What is one of the products always going to be? Each and every time.
Water.
Water. What's left, Kevin?
Magnesium chloride or magnesium, I don't know.
Magnesium chloride.
Yeah.
Okay. Now, remember I said that acids react with carbonates and bicarbonates to make CO2. But it's an acid-base reaction overall. It has to make water. So when we're looking at this, if we make CO2, that makes how many oxygens left over? Look at the bicarbonate. Look at the HCO3. If I take CO2 out of that, what's left? If you take
just
H
one oxygen, right?
and
Oh,
HCO.
and the whatever Na is, I can't remember.
No. I'm just saying HNO. It doesn't matter what the Na is. Okay? It doesn't matter what the Na is. I'm talking about the anion, the polyatomic bicarbonate anion.
Oh, so
HCO3.
hydrogen and oxygen.
Hydrogen and oxygen. And remember, we said with an acid base, we make water. So we know with a bicarbonate or carbonate, I make CO2. That's one of the products. Because it's an acid base, I make water. Then what's left over? Brooke. I've taken this H. Brooke, you with me? I don't want to pick on Cassidy too much. Jasmina.
Hello.
Hi. Okay. Kevin worked this out and he basically said you have CO2 because that's what happens when you react a bicarbonate or a carbonate with water. Because it's an acid-base reaction, our second product is water. And that means this H2 reacted over here with this HCO3 to make the water and the bicarb. What's left that we haven't touched yet, Brooke?
Brooke or me?
I'm sorry, except Jasmina. Brooke apparently doesn't want to play today.
She said her microphone isn't working.
Okay.
But we haven't touched the sodium or the sulfate.
Okay, you're absolutely right. So what I'm going to do here is I'm just going to stop this for a second and put in what we know. We have NaSO4 plus water plus CO2. Then at this point, we have to balance it. Okay? We have to balance it, and the sodiums are good. The SO4s are good. Now we have to balance it 1-on-1. We have one C on the left, one on the left, one on the right. So C's are good. Let's look at our H's. We have 2 H's here. We have 3 over here. So we are going to have to put at least a 2 over here. We have 4 H's over here now. I could put the 2 over here, but that's never going to equal the right side because this is going to always be an even number. And if this number is odd, this will always be an odd number. So what I'm going to do is I'm going to put a 2 there. Okay? There's one thing I haven't done, and that is I haven't balanced the NaSO4. If I look at that now, that reaction is balanced. Questions? So, getting down to neutralization of both hydroxides and carbonates and bicarbonates. If you have a hydroxide, it's easy. One of the products is going to be water. The other product is going to be what you didn't use from the water. In other words, the other cation and the other anion. If you have a carbonate or a bicarbonate, the products of an acid and a carbonate or bicarbonate are going to be CO2. It's an acid-base reaction, so you're going to also have water. And if you look, you've used up the H's, you've used up the CO's, there's an extra O around. What is left is the cation from the second one, the cation from the carbonate or bicarbonate, and the anion from the acid. Anybody need this explained further? Are we good? Yes, you're going to have to know that carbonates and acids make carbon dioxide and water. You're going to have to know that. You are going to have to know if you put an acid with an active metal, then it makes hydrogen and a salt. Any questions, guys? All right. Why do they tell you to stay out of the water when there's an electric storm? Why? If there's
So you don't
thunder.
get electrocuted
Why, Kevin?
because it conducts an electrical current.
It doesn't. It does not conduct electrical current. Okay, you see the screen up here.
It carries electrical current.
If you have water, it will break down to H plus and OH minus. But the product of the concentration of H plus times OH minus is equal to 10 to the minus 14. That's not a whole lot. That's a decimal followed by 13 zeros and a 1. That's what you get when you get the H plus and OH electrolytes. It is not a very, very high number. The reason they tell you to stay out of the water when it is a thunderstorm is because of the other things they're throwing in the water. They're throwing chlorine in there. They're throwing potash. When you're going in a swimming pool, they're throwing all these things to try and keep the pool sterile. But when they do that, they create all kinds of electrolytes. And it's those electrolytes that are going to kill you. It's not the water. For pure water.
What about the sea?
Same thing, even worse. Because seawater has a lot of salt in it, doesn't it, Kevin?
Yeah.
It's the ions from the salt that are conducting the electricity. If you have pure water, the H plus concentration is equal to the OH minus concentration. which is equal to a decimal point, 6 zeros and a 1. Now, if you go to your tap right now and you pour water into that tap, and then you go and check the pH of that, it's going to be 5. But I said it was 7. The difference is when you have water, you have carbon dioxide from the air, which is dissolved in that water. The carbon dioxide reacts with water to make carbonic acid, which has a pH of 5. So it's not the water that's making the tap water slightly acidic. It's the fact that there's carbon dioxide dissolved in it. Okay. So water itself doesn't conduct electricity. The concentration of the ions is too small to really conduct a lot of electricity. What we're talking about is if we put an acid into an aqueous solution and it is a strong acid, what happens is if it's a strong acid, the cations that I'm going to represent with these little purple things separate from the anions, whatever anion is making the acid. They separate out almost 100%. So we got a whole bunch of H pluses in there. We get 100% dissociated. Is this going to conduct electricity? Gabe,
Yes.
are you saying yes, it will conduct electricity? Are you saying yes, I'm here? Same answer for either case.
Yeah, both.
Yes, because an electrolyte is something that has ions in solution. If you have a strong acid, what's happening is you have dissociated the hydrogen away from its anion. That means it's going to conduct electricity. On the other hand, if you have a weak acid, what a weak acid does is it dissociates. Some of them will dissociate, like we have these two, we have these two, we have these two. Some of them dissociate, but for a large extent, the rest of them just stay stuck together. So we have less dissociation with a weak acid. Because of that, we get very little conductivity. Only a fraction of the molecules are dissociated. Because of that, it's not a lot of ions in solution. It doesn't conduct electricity very well. Are we good with everything so far, guys? Now we're going to get into some baby math. How many of you are familiar with logs?
I am.
Is there anybody that's totally unfamiliar with logs? Because, guys, you are going to need them. You're going to need them here for doing pH, and you're going to need them in the future when you're going to actually take the natural logs. Are we comfortable with doing logs, ladies and gentlemen? Somebody look at Brooke to see if she's comfortable in the discussion.
Yes.
Anybody have any problem with it? So I'm going to fly through this, okay? If anybody has any questions, please ask them. What a log is it's the number that is equal to 10 raised to that power. The log of a number is equal to the exponential number that 10 must be raised to be equal to that number. In other words, I've lost my calculator. I got a crummy one here. Let's see. Yeah, I have it. Okay. All right. Say I have the number 342. I take the log, I take 342 and take the log of that. That comes up to 2.53. So what this means is that 10 raised to the 2.53 is equal to the number I said earlier. I hate using another calculator. Hold on a second, guys. So my number 2.53, the log of 339 is equal to 10 raised to the 2.53 power. So the log of 339 is considered to be 2.53. Do we all understand that concept?
Yes.
Yeah.
All right, so if I have 100, the log of one, since 100 is equal to 10 raised to the 2 power, the log of 100 is 2. Since 0.01 is equal to 10 to the minus 2, the log of 0.01 is minus 2. We're basically understanding that concept, right? We good?
Yeah.
So if you have the number and you need the log, find the log key on your calculator and hit it. Type in the number and hit enter. This is how my calculator works. It may be a bit different for yours. So if you have the log of 240 is equal to X, all you got to do is hit log, type in 240, then enter. The number that comes out is 2.38. That is what X is. On the other hand, if you have the log value and you need the number, you find 10 to the X key on your calculator and hit it, type in the number and hit enter. So if I have the log of X is equal to negative 5.42, I find the 10 to the X button, type in the number and hit enter. That gives me 3.80 times 10 to the minus 6. I'm going to continue if I don't hear questions, guys. So, Cassidy, what is
Yes.
X? What is X in log X is equal to 2.16? Do you have a calculator close to you, Cassidy?
Yes, I do. One moment. Um, 144.54.
I'll trust you on it. Okay. Kevin, I want to know what the log of 1.65 times 10 to the 7th, negative 7th is. Kevin?
I don't know, negative 6.78.
It sounds good to me. Okay. Immediately, to know that you're doing this right, this is 2. This means that your number is going to be to the hundreds place. If it was 3, it would be in the thousands. Okay? Now, generally speaking, when you're doing a log, if it's a negative number, then you subtract 1 from it, and that should be approximately what your log number is, just to see if you're entering the numbers right on your calculator. Now, the reason we're bringing that up is pH, by definition, is negative log of the H plus concentration. Remember, we said that H plus times OH minus has to equal 10 to the minus 14. So if the OH minus is 1, the H plus concentration has to be 10 to the minus 14. That sets the highest limit for the pH. Okay, does that make sense to you? On the other hand, if the H is 1 and the OH is 10 to the minus 14th, then we got the log of 1, which is 0. That explains why the scale goes from 0 to 14. So the combination is that if you multiply the concentration of H plus by the OH minus, you get 10 to the minus 14th. That explains why the scale is 0 to 14. So pH is equal to negative the log of H plus. If the combination of the two is equal to 10 to the minus 14th, and they're equal, in other words, they are neutral, then the H plus is 10 to the minus 7th times the OH minus, which is 10 to the minus 7th. Then the negative log of 10 to the minus 7th is equal to 7th. We are at neutrality. Are we good with this basic understanding? pH scale. If we have a whole bunch of acid, the H plus concentration is going to approach 1. Therefore, we have a pH of around 0. If we have very, very little acid, that means the pH of the concentration of the H plus is going to be 10 to the minus 14, which means the negative log of that is going to be 14. That's why the scale goes from 0 to 14. When the OH and the H are neutral, about the same concentration, they're at 10 to the minus 7th. The negative log of the H plus concentration is going to be 7. That's why the pH of neutrality is 7. What's the pH of a basic solution that has an H plus concentration of 8.32 times 10 to the minus 9th? Okay, what we're really doing is we're taking the log of that concentration, we're getting a negative number, then we're just making that negative number positive. Work on this, guys. You should have your calculator somewhat handy. What is the H plus concentration of an acid with a pH of 3.75? Anybody have an answer for me yet?
Is it negative 0.754?
No. Remember, we're not taking the log of 3.75. In order to go from what the pH is to the concentration, we have to take this number first, Cassidy, and we have to make it negative to equal the log of the H plus concentration. Okay? Then the next step is take this and raise it. 10 up to the negative 3.75 is equal to the H plus concentration. So what you probably did, Cassidy, was you probably hit log and then 3.75. Is that correct?
Yes.
What you need to do is you need to make the 3.75 negative first. Then you take 10 raised to that negative power. If we do that, we end up with 1.78 times 10 to the minus fourth molar. Guys, when you do these things, pH is always going to be in the range between 0 and 14. The H plus concentration is going to have an exponent anywhere from -1 all the way up to -13 or so. Okay? So I'm going to throw in another slide here. That hopefully will help you out. Okay, two simple rules. Guys, I'm going to resave this for you. If you have the pH and you want the concentration, make the pH negative, hit the 10 to the X button, then enter the negative pH. If you have the concentration and you want the pH, hit the log button, enter the concentration, then enter. Make the number positive. Very simple rules, guys. Okay? Everybody have your calculator out. It should not take you that long to do these problems. What is the pH of an acid with the concentration 9.27 times 10 to the minus 2? First person that shouts out an answer that's correct gets a point. Extra credit point.
Negative 1.03.
1.03. Who is this, Gabe?
Yeah.
Okay, Gabe. I gotta see where you're at. Gotta find my thing so I can possibly give you credit.
I got negative 1.24.
Okay. All right. If you have I gave you the concentration, right? So all you got to do, look at this.
Oh, dang.
If you have the concentration and want the pH, hit the log button, enter the concentration, then enter, make the number positive. So 1.03, Gabe, you get a point.
Oh, I was gonna answer the second one, darn it.
I haven't asked the second one.
But the answer's up.
Was it right?
Yes.
Okay. If we're doing the second one, if I have the pH of 12.45, what I do is I make that negative, a negative 12.45. I find my 10 to the X button, push in negative 12.45, and my answer is 3.55 times 10 to the minus 13. Any questions converting pH to concentration, concentration to pH? Any questions thereof? Okay. This is interesting to look at, but honestly, I'm running out of time, so I'm basically not going to go through it in that much detail. And basically, you can see neutrality, and it gives various things: normal rain, natural waters, acid rain, fish populations. Same thing in the human body. For one reason or another, different fluids have different pHs to help different body functions to go along. So we have these different body solutions that happen. Interesting slide. This shows the pH of rainwater across the UH, acid rain. Why do you think the areas, by the way, that's where I grew up. Why do you think the areas in the Northeast have much more acid rain than the areas in the West?
There's more factories.
More industry. The industries are spewing out the NO2 and the SO2, which are reacting with the water in the air to make acids. So basically what happens, I told you already, carbon dioxide reacts with water to make carbonic acid. Now, what is happening in the world in terms of the sea raising or lowering in pH? We're generating from our fossil fuels, we're generating more carbon dioxide in the air. That carbon dioxide is making more carbonic acid, which is then the carbon is dissolving in the water. It's making more carbonic acid. Guys, the coral is made of carbonates. So what happens is you have the carbonic acid reacting with the coral, and it's killing the coral. If we're dealing with atmospheric air coming from factories, we're dealing with mainly nitrous oxide, which reacts in the air to make nitric acid, or we have SO2 or SO3 reacting with water to make sulfuric acid. Guys, these are two of the strongest acids we know. So therefore, what is happening is we're creating all of these vapors, we're creating acid rain, and it's not good. Okay, another subject. When life goes either way, we create amphoteric substances. So, is there an H on CO3? Cassidy, is there an H on CO3?
Yes.
So could this lose the H to make H plus and CO3 minus minus?
Yes.
By the same token, can this accept another H and make it a neutral molecule, H2CO3?
Yes.
Which means it's accepting a proton, which means that it is a base. So we have things that can accept the proton and also lose a proton. If that substance can accept the proton or lose a proton, then it's something called amphoteric. It can act like a base under one set of conditions. It can act like an acid under other sets of conditions. It's amphoteric. Now, proteins are made of compounds called amino acids. If you put an amino acid in water, You're not used to this yet, but you will if you're getting into organic chemistry. If you have this thing, it's called a functional group, a carbon, oxygen, oxygen, hydrogen. What can happen is this OH can lose a hydrogen to make a negative portion of the molecule, an O minus. It has donated a hydrogen. But within that same molecule, this N has a pair of electrons. So that hydrogen that has a positive charge can drift down here and make this NH3 plus. This is a basic portion. So amino acids, even within the same molecule, we can have an amphoteric situation. It doesn't have to be one molecule to another molecule. It can happen within the same molecule. All right, I got 10 minutes left. We're definitely not getting to gases, which probably means that our test is going to be rescheduled. I will make that announcement later. I'm looking right now at the schedule, and I'm seeing that test 2 is due Tuesday the 6th. It will probably be Thursday the 8th. That means I'm going to have to rearrange the quiz schedule too, guys. All right. Now, the main problems we're dealing with in acid bases, the thing you are dealing with in the standardization of your base today. We're taking a known volume and concentration of one of our reactants, either the acid or the base. We are reacting it and taking it to neutrality, to where the phenolphthalein is pink. When the phenolphthalein is pink, we know that the H plus is equal to the OH minus. So at that point, we have a known quantity. If I take a volume of my NaOH solution, and I know what its concentration is, can I not determine the number of moles of NaOH? Guys? Little feedback here. If I have a known volume of my NaOH and I have the concentration, can I not make a determination of the moles of the NaOH?
You can.
So I have the moles of NaOH. Do I not have a molar ratio between my NaOH and my acid?
Yes.
Therefore, I can take that molar ratio and change my moles of NaOH into moles of H2SO4, correct?
Yes.
Now, the hard part of this is you have to understand that all those moles of H2SO4 had to be contained in the volume of the H2SO4 you added. So if that is true, then all you have to do is take the moles of the H2SO4, divide it by the liters of your H2SO4 solution. That will give you the concentration of your H2SO4. Have I said anything outrageous here, guys?
No.
Are we able to follow along with what I just did? Because I'm going to go through in a second and actually fit in the numbers.
Just for a question, I don't think it has to relate to this, but just because it gives us like the moles and the volumes, like would we, I'm assuming, not be able to use like
Let's use, I'm sorry, Cassidy, I'm sorry. Let's use correct terms, not the moles in the volume.
the molarity.
Molarity in the volume. Okay, now I'm sorry I interrupted you. Ask your question.
So we couldn't use like M1V1 equals M2V2 on this and just find what M1 was?
I'll get into that in a second.
Okay.
All right. Just give me a few minutes. I got 5 minutes left, okay? So what I would do if I'm doing this equation, I write out the overall reaction. I then put what I know about each of the reactants under it. So I know that I'm keeping the same numbers together. I'm looking at this. I can multiply the milliliters times the 1 liter over 1,000 milliliters, and you're going to get tired of using this conversion. Eventually, what you're going to do is you're going to say, oh, all I have to do to change milliliters to liters is move this 3 spots over to the left. So I'm going to take my 0.02250 liters, multiply that by my molarity, and I get 0.002666 moles of the NaOH. I know my molar ratio. I got 1 mole of H2SO4 for every 2 moles of NaOH. This means I have 0.00133 moles of H2SO4, but that was in 15 milliliters. So I'm going to divide my moles by my liters of H2SO4, and I'm going to end up with a concentration. Now, Cassidy, what you're proposing is absolutely correct. If and only if the coefficients in front of the acid and the base are equal to one another.
Okay, so if it was like 2 H2SO4 and 2 NaOH.
If it was H2SO4 plus BaOH2.
Okay.
Both of them have coefficients of 1 to 1, then yes, you can do what you proposed. And
Okay.
guys, I will get into that in more detail. You can do that, Cassidy, because you don't have to go through the molar ratio step.
Yeah.
But it's only if the coefficients in front of the acid and base, or in other words, the number of H pluses is equal to the amount of OH minuses. Does that make sense to you, Cassidy?
Yeah.
Okay. Again, I titrate. Okay, if I'm doing this experiment in a laboratory, what I would do is I would take my burette and deliver 12.50 milliliters of my phosphoric acid into a flask. Then I would take that flask, put it under my base. Then I would do it drip by drip, stop it. I noted my initial volume and my final volume. I subtracted the final from the initial, or the initial from the final. I ended up with 17.00 milliliters. I noted what my original concentration of my base was. So if that's the case, then all I have to do is take my volume of my base, change that to liters, which I got lazy and just move the decimal down here, multiply that by my concentration of base, that gives me my moles of barium hydroxide. I then take my moles of barium hydroxide, turn that into, and this is, damn it, this is wrong. This should be, this should be 2 to 3. Okay, that should be 2 to 3, 0.04250 times 2 divided by 3 equals, this should be 0.002833. I then divide that by 0.01250, and I get 0.2. Two, 6, 6, 7. Any questions about this? Any questions about doing it? Titrations. I'm here for you guys. All right. An equivalent weight is the mass required to deliver 1 mole of something. Right now, we're talking about acids and bases. So the equivalent weight is the amount that will deliver 1 mole of H pluses or H3O pluses. If I had 36.5 grams of HCl, there's a 1-to-1 relationship between the moles of HCl and the moles of H plus made from the HCl. 36.5 is 1 mole of HCl. I can make 1 mole of H plus from that. Therefore, the weight to deliver 1 mole of HCl, 1 mole of H plus from HCl is going to be 36.5 grams. Are we good with that understanding, guys? If I have 98 grams of H2SO4, how many moles can I deliver? How many moles of H3O plus how many moles of H2SO4 do I have? The molecular weight of H2SO4 is 98. Kevin?
1.
If I have 98 grams of H2SO4 and the molecular weight is 98, how many moles of H2SO4 do I have?
1.
Okay. So how many moles of H3O plus will 1 mole deliver?
1.
How many H's do I have, Kevin?
2.
So if I have 1 mole of H2SO4, how many moles of H3O will that produce?
2.
Do you see that, Kevin?
Yeah. No.
How many H's does my H2SO4 have?
2.
Okay. So how many can it deliver?
2.
So if I have 1 mole of H2SO4, it can deliver as many as 2 moles of H3O plus. Okay? Does that make sense? So
How
if
come
I
it's
have,
not a ratio? Like,
sorry,
well, if you have 3 H's in the end product.
we're going to get to that in a second. I'll show you that in a second, Kevin. So if I have 49 grams of H2SO4, how many grams do I need to deliver 1 mole of H2SO4? If 98 is 1 mole and 1 mole delivers 2 moles of H plus, how many grams of H2SO4 do I have to deliver 1? We've already said that 98 grams will deliver 2, right?
Yeah. So you just divide it by 2.
Okay. This is basically what we're saying. Sorry, I'm doing this. 98 delivers 2, right? True, Kevin?
Yeah.
So don't we want to say We want to know what the weight is that will deliver 1. Isn't that expression not true?
Yeah.
So what's my answer, Kevin?
49.
Okay, 49, yes. So what is the equivalent weight? How many grams? If 98 grams of H2SO4 will deliver 2, how many grams will deliver 1 mole? You just said it, Kevin.
Yeah, 49.
So the equivalent weight of H2SO4 is 49. All right? Let's consider H3PO4. If I have 98 grams of H3PO4, how many moles of H3O plus will it deliver? Again, it just so happens that the molecular weight of H3PO4 is also 98. How many H's, Kevin?
3.
So how many moles of H plus will H3PO4 deliver? If there are 3 H's, Kevin, in one molecule, how many H pluses are possible out of that?
3.
So if I have 1 mole of H3PO4, how many moles of H plus do I have?
3.
So if I set up that same ratio, if 98 grams will deliver 3, how many grams will deliver 1? What's the answer to that, Kevin?
32.
32 approximately.
0.66 or
32.66. I'll grant you that. So because H3PO4 has 3 hydrogens, its equivalent weight is 32.67 because it has the possibility to deliver 3 hydrogens. When I have sulfuric acid can only deliver 2. So its equivalent weight is equal to 49. Does that make sense to you, Kevin?
yeah.
So ladies and gentlemen, sometimes you're given an acid. Sometimes you're given an acid and you don't know. You're not given the formula. You're just given an unknown. And you're asked to determine a weight. All you can determine is the equivalent weight, the weight that will deliver 1 mole's worth of H pluses, because you don't know what the formula is. Does that make sense to you guys? This is basically what we're doing this week and next week, is working on something called equivalent weights. Is anybody confused about this?
No.
Gabe, Kevin, Jasmina,
Yeah,
and
I'm
Brooke, anybody confused? Jasmina, you good?
Yeah, I'm good.
All right, now the last thing I want to do. Is bring up Cassidy's point, because this will help things. All right. If we're doing a titration calculation that involves equal coefficients in front of the acid and the base, remember, if it's a 1-to-1 ratio, then instead of saying moles of H plus equal moles of OH, then the moles of the HCl are going to equal the moles of NaOH, because we do not have to use the molar ratio here. Now guys, if we know the concentration and volume of the base, we can get the moles of the NaOH by taking the molarity of the base, multiplying it by the liters of the base. So that's going to be our right side of our equation. Then what's going to happen in our titration, we're going to be either given the concentration of our acid and be asked what the volume is, or we're going to be given more likely the volume and asked to solve for what the concentration is. So we can use the formula Ma times Va, which is the moles of HCl and the moles of the NaOH, is equal to the moles of base times the volume of the base. But, and this is an extreme but, you have to realize the acid has to have the same number of H's as the base has OH's. Do we understand that, guys?
Yes.
So as I said, Cassidy, I was going to get to this eventually.
Yeah, sorry, that's just stuck in my head, and I saw like that we had everything but the one, so I didn't know if we could use it for that or not. So
Again, this last little caveat, if you follow this last little caveat, you'll be fine. But if the H pluses don't equal the OH minuses, like for example, if I'm taking nitric acid, HNO3, and I'm reacting that with aluminum hydroxide, AlOH3, I can't use this because my aluminum hydroxide is delivering 3 OHs in each mole of AlOH3. It's delivering 3 moles of OH minus for every mole of H plus delivered by the HNO3. Does that make sense, Cassidy? And I've lost Kevin and Gabe, and Brooke went by long ago.
Yeah, that's super helpful. Thank you. I've just that like kind of formula has stuck in my head, so I've been waiting to know when we were going to use it.
Cassidy, it works wonderfully. As a matter of fact, it's kind of magic when I do this. The one we're doing today, the lab we're doing today.
Yeah.
You don't have me for lab, do you?
No, I have Professor Moore.
Okay. When I go through and I'm doing this face to face, I can look at the volumes of the acid and base that kids have, and I can come up with a number like this. And it's because I'm using this formula.
Yeah, this formula makes things like 1,000 times easier.
You're absolutely right. You're absolutely right. But again, you got to use this caveat. If they don't have the same number, then you got to do it the long way.
Okay. And just for this too, like if we're both like given both the volumes and like milliliters, then we don't need to convert that to liters, or okay.
Absolutely.
Just wanted to make sure, unless it like asks for like the volume in liters
Cassidy,
in the end, convert
Cassidy,
it.
I could give you your base is 0.1 molar and you have 150 ounces, and that neutralized 250 ounces of acid. I don't have to convert the ounces to liters.
Okay, perfect. I just wanted to check.
Because whatever the conversion you use to convert ounces to liters on the right side of your equation, you're going to have to do that same one to the left side. So as long as your volumes have the same labels, you don't need to convert it, which is another one of the easy steps when I do this, when I'm going around with students in the face-to-face lab.
Yeah.
If you're used to doing that, then fine, Cassidy, you're fine with it. If you're kind of a little bit antsy about it, then do it the long way.
Okay. I'm very used to this. I remember using the M1V1 equals M2V2 quite a bit in intro chem, honestly.
And
so
Jasmine has gone away from us. And understand this too, Cassidy.
Mm-hmm.
you can do the same thing. It's not just acid-base reactions.
Okay, that's what I thought. But for those ones though, would it just have to have the same coefficient and not have to worry about like the numbers of
Yes.
H plus compared
Yes.
to OH? So if
Example,
I just have like
And it-
two, like,
let me give you an
the-
example. Let me give you an
Okay.
example. If you mix NaCl with silver nitrate,
yes.
okay? If you mix like 15, if the question is, what is the volume of silver chloride solution needed to react? I'm sorry, excuse me, let's start over. What is the volume of a 0.250 molar sodium chloride solution that will react with 50 milliliters of a 0.5 molar silver nitrate solution? Okay?
Okay.
If you had a question like that, then you know the NaCl coefficient is equal to the silver nitrate because you've done the equation and you balanced the chemical reaction. You know
Yeah.
that that's a one-to-one relationship. So in that instance, yes, you can use M1V1 equal M2V2.
Okay. Cool. That's like my only question then. I've just been like waiting to use that formula because I know I saw it and I know that makes life easier. So
So everything today fairly easy? Nothing,
yeah, I've got that all down pretty well.
I'll be honest with you. The thing I'm going to start on Thursday with is going to be hard to grasp. It's going to involve a lot of physics equations, and it's going to involve some assumptions. And you got to know, you have to know this. This is part of the basic concept. It's a new thing, and it's where we're starting it's where I'm starting to deliver new material.
Okay, and so that doesn't sound like stuff I have done before. I also have never taken physics, so this should be interesting.
I give you the equations.
Okay,
Okay.
perfect.
And there are things like force is equal to mass times acceleration.
I might have done just a little bit of that, honestly, in like the very end of my AP chemistry class, but that was like 5 years ago at this point, so it's been a
No
while.
problem. No problem. I will try and lead you through the process. Okay.
Okay, thank you.
No problem. Since you're the only one here, if you're good, I'm good.
I am good. Thank you so much for going over that with me.
No problem at all.
All right, have a good day.
You have a good day too.
Thank you.